Hi, and welcome to UNSW, the School of Mathematics and Statistics in particular. My name is Thomas Britz, and I'd like to look at problem 99 in the course MATH3411. In this problem, we have to look at a digital signature scheme. So this common one here, DSS. And here we've got Alice, who wants to send messages and sign her messages in such a way that we can be sure that it's, or fairly sure that it's actually coming from her. Well, the messages are coming from her. So the way that this works is that Alice has a private key and uses this to generate a public key. And that's the first thing that we have to do. We have to find this public key. We have a couple of parameters, and in fact DSS, and this is just a simplified version of it, has a lot of parameters and it can get a bit confusing, but let's see how we go. So we've got two prime numbers, Q and P, and then we've got something that quite often we've used G for a primitive element. Well, this is not quite a primitive element. Here 15, if we raise that to the power of 12, we get 1 mod 53. So it's not primitive, but it will perform some of the same flavoured roles as a primitive element in many of the previous questions. So to find the public key, all we have to do is raise G to the power of E and reduce this. So G was 15 and E was 7. And then we have to reduce this mod P, or in other words mod 53. And there you get 42. So the public key is, in this case, 42. So we found out in part A that Alice's private key was 7, Alice's public key was 42, and then we can use 42 to then verify her signature if she is to send something. We'll do that in part C. In part B, however, Alice is going to send a message and then generate a signature along with that message. So the first thing that needs to be done is is that Alice has to choose a random number X, and she will then send a message that gets hashed. So we don't need to use the whole message to generate a signature. We can just hash it. For instance, here we have the hash value 9. And then we have to calculate Alice's signature. So this is not too complicated either. The signature will come in two parts, but for that we need a third variable, which is as follows. So y is going to be a bit like k, is going to be g to the power of something, but this time it's going to be g to the power of x, not e. So this is G, which was 15, to the power of 5, and this is mod 53, again P, and that gives you 44. So now we can derive the signature in two parts. The first part is R, which is just equal to what you get if you take y, which was 44. But then you now reduce it mod q. So q was this smaller prime. So if you do that, then you get, if we move it a little bit here, 44, then we get 5. So that's half of the signature. The second half of the signature is S, and that's a bit more complicated. It's the inverse of X times H plus E times R. So this depends on quite a few variables here, and this is going to be mod 13 as well. Now X inverse, well 5, and this is all going to be mod 13. So we have to find the inverse of 5 mod 13. And that's luckily not too hard to do. We could use the Euclidean algorithm forwards and backwards. But if you notice that 5 times 8 is 40, which of course is just 1 mod 13, then we find that x, or in other words 5, the inverse of that is just in fact 8. So that's not too hard. So we have that x inverse is 8, h was 9, e was 7, r we've just calculated to be equal to 5. So you have 35 plus 9 is 44, so that's congruent to 8 times 44, and this is still all mod 13. And 44 mod 13 is 5, so we have 8 times 5 is 40, which in turn is just 1 mod 13 again. So apparently S is 1, and our digital signature is just the pair R and S, or in other words 5 and 1, and that is the answer. So that's this pair is the signature. Now in the third part of the problem, Alice sends, or Bob receives a message, and it's possibly from Alice, who knows, but the person sending it might be Alice or someone else, but they're certainly using the same public key here, so if they're not Alice, they're pretending to be. Now they are sending a message where the hash is now equal to 10, the hash value of that message is 10, so the signature might be different. It won't be, as before, 5,1 necessarily. That's okay. Here we have a signature that relies on this hash value as well. Bob would like to know whether this signature is Alice's signature, whether it's genuine or whether it's valid. Does this message that's got that hash value, does that come from Alice? So that's what we have to find out. Again, we have to find a number of values, and actually quite a few values in this part of the solution. So here, R and S, we have some values there. R is equal to 2, S is equal to 4 here, and then we've got H is equal to 10. So we need to calculate some numbers, some two U numbers, U1 and U2, and they are equal to the inverse of S in both cases, times, well, in the one case it's times H, and in the other case it's R. Now all of this is mod 13, or in other words Q. So mod 13, mod 13. So in order to work out what that's equal to, we need to find the inverse of S, which is 4 mod 13. And you can see that that's the same as 10, for instance, because we've got, so the inverse of S is 10, because we've got 4 times 10 is 40, which is congruent to 1 mod 13. So this is 10 times 10, or 100. And down here it's 10 times R, which was 2, which is 20. So here we have 9, and here we have 7. Yep, cool. So we've worked out these two values, U1 and U2. Now what do we need them for? Well, now we're going to work out a third value, Z, and that's equal to now G raised to the power of U1, and then K, and there's the public key making its appearance, to the power of U2. So that's 15 to the power of 9 times K, which is 42, to the power of 7 and you then work out what this is. But in the first instance, this is actually mod, what's it called, where was it, 53. And when you work out what that's equal to 24. So the next thing that you do is you take that 24 and then you reduce it mod 13. So you get 11 mod 13, and 11, then we have to compare that to R, and that's not equal to R. So this shows us that this signature is not valid. So the answer is no. That is not a valid signature. So presumably this is not from Alice. And there we're done. Thank you very much.